Well, hello everybody. Hope everyone's doing well. Hope you had a good weekend. It is ninth week, so just a little bit of time left. Does anyone still have a midterm this week? Okay, those are always the. It's always just like midterm in ninth week, right? It's like why? But that's quarter system, right? Okay. Ooh, something is happening. Okay, so you guys do have a quiz tomorrow. I did post kind of like a little formula sheet online, I think. I don't know, maybe you saw that. Basically, you don't have to memorize all of the standard error formulas and test statistic formulas and things like that. I will provide that to you as part of the quiz. I'm thinking of also posting like a practice quiz today. Okay, so keep an eye out for that. It'll probably get posted by maybe 4:30 or 5 o'clock. Okay, just please bear with me with a little bit of patience, because I want to make a practice thing, but that's not exactly the same as the actual quiz. Yeah, question. Okay, you're gonna have to like yell because I can't. It's going to be chapter 8 plus confidence intervals, which is the last bit of chapter 7. Okay, so a little bit of chapter 7 and chapter 8. Okay, and so I'll post a practice quiz for that because you guys said the practice quiz last time was helpful. So just trying to be helpful. That's all. You're welcome. And okay, and so today we are going to cover chapter 9. Okay, and I forgot to have reference tables printed out. So for today, I will just show the reference table on the screen, and then on Wednesday I'll have paper copies to pass out for you guys to use. Okay. Okay, so let's begin. Chapter 9, we are going to do inference for numeric variables. Okay, so with chapter 7 and with chapter 8, we did inference for categorical variables, and we were dealing with proportions. In this chapter, we are dealing with numeric variables, and we will do inference with sample means. Okay, so let's see. Okay, so let's see, numeric variables. Okay, so we will, I'll just write sample means. Okay, so again, just kind of comparing chapter 7 and chapter 8, we were dealing with sample proportions because we had categorical variables. All right, so let's just list off symbols that we will use. Okay, so when we are dealing with the sample, we have statistics. Okay, so we have the sample mean, x bar. And we have the sample standard deviation, S, okay? And then when we are dealing with the population, we have parameters, So we have the population mean, mu, and the population, I'm going to just abbreviate, standard deviation, sigma. Okay? So we have mu and sigma. Okay. Let me just get this saved. Week 9, Monday. Lecture 3. Okay. All right, and when we were in chapter 8, we talked about the central limit theorem and how we could approximate the sampling distribution of p hat with the normal distribution, okay? So, so I'll just write recall. In chapter 8, the central limit theorem, and I'm hoping this is familiar, says that the sampling distribution of p hat can be approximated with the normal distribution, okay? In chapter 9, we have something very, very similar, okay? And this is actually the kind of the point of the lab that has been assigned this time around. It's the lab on the pennies. You're basically doing a sampling distribution for a numeric variable, okay? So in chapter 9, we have, we still use the central limit theorem. Okay, and it says the sampling distribution of the mean, okay? So if I'm talking about the sampling distribution of the mean, am I talking about x bar or mu? Sampling distribution of x bar, okay, can also be approximated with the normal distribution. Okay. All right, and so so kind of the big picture, and I'll use you know our the lab that has been assigned. You know, the population for the, I don't know, age of pennies might be something like this. Okay, so this is the age of pennies population. So the population is skewed or whatever, okay? And again, the idea is from the population, you know, we're going to draw, you know, sample 1 and get an x bar. And then from this population, we get same population, we get sample 2. And we get another x bar, and we keep drawing more and more and more and more, okay? So we get more x bars every single time we draw a sample. Okay? And again, we keep track of every single x bar that we observe from the population, okay? And this is, with Fathom, you can do this, right? You're just going to resample from that population of pennies. Every time you draw a sample of pennies, you calculate an x bar. You're collecting the measures, and you keep track of all of these things, right? this is what was covered in the lab, right? I'm not just, okay, I just want to make sure. Okay, all right, so, so when you do this, you know, so this is the, here's the population over here. This is what the population looks like. The population does not look like a normal distribution, and yet when we keep track of all of the x bars, oops, x bars, we get a sampling distribution. Okay, and so the sampling distribution ends up looking like a normal distribution. Okay, so this thing, this is approximately normal. Okay, the mean of this thing. Okay, so if the population has a mean like I don't know, let's see, right here, then the mean of our sampling distribution is going to be mu. Okay. Sampling distribution is mu, okay? And then the standard deviation of the sampling distribution is sigma divided by the square root of n, okay? And so here we are saying that yeah, the spread of our sampling distribution depends on how big our sample size is. Okay, so and this makes sense. Okay, so the spread or the sigma or standard deviation over the square root of n, okay? So this depends on the size of the sample. And what we see is that larger samples will reduce the amount of spread in the sampling distribution of x bar, okay? Okay, and if we just think about that for a little bit, I think it makes sense, okay? Because if you have a small sample, let's say you're taking samples of size 2 or 3, okay? You're taking just, let's say you're going to pick 3 random people, okay? And let's say we're going to measure the average, the IQ of these 3 random people, and then the thing you're measuring is the average of those 3 random people, okay? When you pick 3 random people, it's not going to be super likely, but it's quite possible to get pick people at random and get 3 people with very high IQs, and therefore your average of those 3 people would be high, okay? And it's also very possible to get 3 random people where the average IQ is quite low. You could get 3 people and all of them happen to have low IQs, and therefore the sample average is quite low. On the other hand, let's say you're picking 100 people at random. If you pick 100 people at random, it's going to be very, very, very unlikely for all 100 people to have very high IQs, giving you a high X bar, giving you a sample average that is high. Okay? Conversely, it's also going to be very unlikely for all 100 people to have low IQs, giving you a sample mean that's quite low. Okay? So when you have 100 people, you're probably going to get some that are high, some that are low, and they're all going to kind of balance each other out, and the average of that 100 is going to be quite similar to the average of the population. But when you have a small sample, like a sample of size 2 or 3, it's quite possible for all, for both or all three of them to be quite high or all three of them to be quite low, giving you, more spread in the different X bars that you might observe. Okay? Does that make sense? And I think that will also be demonstrated in your lab when you do the pennies simulation here. Okay. All right. So basically, we can say the distribution of X bar is approximately normal, and we'll say X bar comes from something like a normal distribution with a mean of mu and spread sigma over the square root of n. Okay? So far, so good? All right, so let's just try an application of this. Okay. Okay, so I'll write up a question here, and I think we'll be okay. So we'll say, I don't know, the average weight of I don't know, of a dairy cow is, and I'm making this up. I have no idea, okay? 1,100 pounds. Anybody familiar with dairy cows and how much they weigh? Huh? 110 pounds? 1 ton? 2,000 pounds? Something around there? Now I'm curious, because that sounds really, really extreme, okay? All right, so we'll say average weight of dairy cow. Okay, look, it's already, okay. Holstein, I didn't even know there were these kinds of dairy cows. All right, we'll go with Jersey cattle. We'll split the difference, 1,500 pounds, okay. All right, dairy cow we'll say is 1,500 pounds. With a standard deviation we'll say 150 pounds. Okay, so we'll say you decide to select a random sample of 9 random cows. Okay. I guess the 9 is random is redundant. Okay. I'll say, what is the probability that the average weight of these 9 cows is over, we'll say 1,600 pounds. Okay, so we're going to ask, what's the probability that the average weight of these 9 cows is over 1,600 pounds? Okay, so now let me put up some clicker options here. And oh dear. Okay, let me. I need my Z table. Okay, I hope I did my mental math correctly and that the correct answer is available here. Okay, I'm gonna fire this up. Okay, just a few more seconds here. Give until okay, I'm gonna hit stop. Okay, so let's see. Okay, so what we have here is we are looking at the distribution of x bar, okay? And we know that x bar comes from a normal distribution with a mean of mu and a standard deviation of sigma over the square root of n, okay? And so here we're talking, up here this is the population, and we're going to say that the average weight of the cow is 1,500 pounds, which is going to be mu and has a standard deviation of 150, and that's going to be our sigma, okay? And here we're looking at a random sample of 9 cows, and so this is going to be my n, okay? And here we're talking about the average weight of these 9 cows, which is our x bar, okay? So here we've got x bar coming from a normal distribution where the mean is 1,500 and the standard deviation is going to be 150 over the square root of 9. So this is 150 over 3. We get a standard deviation of 50. Okay? And so at this point, we have a normal model problem. This is now the sampling distribution of x bar. So this is not the distribution of individual cow weights. It's the distribution of means of random samples, okay? So we've got 1,500 and we want to know what's the probability that the average weight of all 9 of these cows, so it's not what's the probability that one randomly selected cow is over 1,500 or 1,600, it's the probability that the average of all 9 of these cows is over 1,600, okay? So at 1,600, our z-score is going to be 1,600 minus 1,500, the mean, divided by our standard deviation of 50. Not 150, but 50, okay? So we get a z-score of 2 now, okay? And then when you look up the z-score of 2, and you subtract that from 1, you get 0.0228. So our answer is going to be B here, okay? All right, so it seems like some of you guys got a little bit mixed up and you picked, you did not take into account that we're looking at the average of the nine cows, okay? The average of the 9 cows reduces our spread from 150 down to 50. Okay, question, yes? I could only kind of hear you. I think the question was if we took a different sized sample, or? Yeah, let's say you don't specify about yeah, so so here we can only talk about the average weight of a sample, okay? So you need to specify some kind of sample size, okay? You can't just say, what's the probability that the average, like here, because it says we're saying the average weight of a dairy cow is 1,500 pounds in the population. So the question, when we ask what's the probability that the average weight, and if we're not specifying a sample size and we're just talking about the population, then there's no, the question doesn't make sense anymore because we know that the average weight in the population is 1,500. But when we're talking about a random sample of 9 cows or a random sample of 50 cows or a random sample of whatever, we can then specify, what's the probability that the average weight of our sample, of our random sample, ends up over a certain number. So here, it's very similar to what we did before, okay, except now we are dealing with x bar rather than a p hat, okay? And then the way we calculate the standard deviation is different, okay? But in terms of the concept of dealing with a sampling distribution, this part is quite similar to before, okay? Is that okay with everybody? Okay, so in the same vein, because we are dealing with a sampling distribution now, and we can say that the sampling distribution of x bar follows a normal distribution, we can then do the same kind of inference that we did with p hat. Okay, so with p hat we created confidence intervals and we did hypothesis tests. When we're dealing with sample means, we can also create confidence intervals and hypothesis tests. So first I'm going to start talking about confidence intervals and hypothesis tests, but I just remembered another important part is checking the conditions for use of the central limit theorem. Okay, so let me just cover that here, okay? All right, so we've got conditions to use the central limit theorem for numeric variables. Okay, so I almost forgot. Okay, so as far as the conditions here are almost exactly the same as they are for categorical variables, okay? So one is the sample must be selected randomly, okay? Sample is random. Okay, and then members members in the sample are independent of each other. Okay, so we can just call this the random and independent condition. Okay, so that's the same as before. What were the other conditions to check the central limit theorem? We had the large sample condition, right? When we were dealing with the categorical variable, we said you needed to have at least 10 successes and at least 10 failures, or that n times p had to be bigger than 10 and n times 1 minus p has to be bigger than 10, okay? We don't have that anymore. So for the large sample condition, basically it's just n has to be, quote, large enough, all right? And this is vague, and that's because we don't have a very good way of defining what large enough is. So there's kind of two ways, okay? So if the population is normal or nearly normal, so if the population is normal or at least unimodal and symmetric, you know, basically any sample size is big enough. Okay? On the other hand, if the population is not normal, so if the population is skewed or otherwise is not normal, let's say it's skewed or something, okay, then n should be larger. And n needs to be larger. In general, this is a rule of thumb. N equal to 25 or more, greater than or equal to 25, is big enough for most purposes. Some textbooks say 30, greater than or equal to 30. Okay, but in extreme circumstances, 25 is not big enough. Okay, but if it's very skewed, then 25 still might not be big enough. Okay, so you know, things like income is really skewed, so 25 is not going to be big enough in that case. All right, but most other cases, 25 is usually big enough. That's kind of our rule of thumb. And all this is to say you can use the central limit theorem for the sampling distribution of x bar. Okay, use the you can approximate the sampling distribution with a normal model. Okay. All right, and then the last condition, big population, same as before. Population needs to be at least 10 times the sample size. Okay, so these conditions are the same as before. The only thing that has changed is the large sample condition. You want to we're not looking at n times p anymore, or successes and failures. It's just, if the population is normal, you can have samples of size 4, okay? Or size 3, anything, really. If the population is normal, you can have tiny samples. And if the population is not normal, you want samples of around 25 or more. Rule of thumb, okay? That's what we got. Okay, so then, so let's talk about creating a confidence interval. Okay, so let's just do a brief recap. So recall confidence interval for p hat. Okay, not p hat. I'm sorry, for p based on a sample. Okay. So when we create a confidence interval for the population proportion p based on a sample, what do we put in the middle of the confidence interval? P hat goes in the middle, right? This is the middle of the confidence interval. And this is basically our current best estimate of p. Okay, so based on the data we have, our current best guess of what p is p hat. Okay, so that goes right in the middle of our interval. Okay, and then we go plus or minus the margin of error. And how do we calculate our margin of error? It's critical value z, right? Critical value based on the normal distribution. And we multiply this by our standard error, right? And what's our standard error? The square root of p hat times 1 minus p hat divided by n, okay? Our standard error. Okay, and we use p hat. Why do we use p hat instead of p? Because we don't have p, right? Okay, I'm hoping this looks familiar. Or am I hoping for too much? Okay, well, so anyway, and here we say, you know, and then we say I'm blank % confident that p is between here and here because we're counting on the fact that our random sample p hat ended up close to being near p. Okay? All right, so using kind of the same ideas, okay, let's make a confidence interval for mu based on a sample. Okay, so in the middle of our confidence interval, we're going to put our best guess of mu. What's our current best guess of mu? Okay, what would that be based on our data? What's that? X bar. So X bar is going to go right into the middle of our confidence interval, okay? And then we will go plus or minus, and then what should we do? Huh? Okay, well, we're going to put in a critical value. Okay. And so I'm going to just do a temporary, okay? So I'm going to just call this a z, all right? But this is not the real thing that we use, okay? And we're going to multiply this by our standard error, okay? What is our standard error? Okay, so in the central limit theorem, we learned that the sampling distribution has what standard deviation? Sigma over the square root of n. Okay. All right, do you guys see a small problem here? So over here, we had to use p hat because we didn't know p, all right? What do we know sigma? What is sigma? So sigma is the standard deviation of the population, right? And here, what we're saying is that, well, we don't know the mean of the population. Do you think we're going to know the standard deviation of the population? Probably not, okay? So there is a problem here, and it's that, okay, problem, we do not know sigma, okay? Okay, so what should we do? If we don't know what sigma is, can we replace sigma, the standard deviation of the population, with another value? Okay, well, what we're going to do, what we're going to have to do is we're going to have to put in our best guess for what sigma is, okay? And so our best guess for sigma is going to be the standard deviation of our sample, okay? So we will replace this, or we will plug in our best guess for sigma, okay, which is our sample standard deviation S. Okay. All right, so this results in, okay, so the end result is going to be x bar plus or minus, and just go with me on this. Instead of z, it becomes a t, and we're going to multiply this by s divided by the square root of n. Okay. So why am I changing this to t? Okay. So when we were dealing with categorical variables, I said if we replaced p with p hat, mathematically it's okay, right? Like in the end it works out, we can just keep everything the same, okay? The story changes when you replace sigma with s, okay? So again, math beyond the scope of our course, but when you replace sigma, the population standard deviation, with the sample standard deviation, okay, it introduces a bit of uncertainty into our equation, and so we have to compensate for that by using t rather than z, okay? So t is kind of like is our critical value, but it's a compensated critical value, okay? So I'm going to just write our critical value t compensates for using s instead of sigma, okay? All right, so we're gonna, we're just about to run out of time here, okay? Rats, okay. All right, well, I guess on Wednesday I'll print out the reference table for T, and then we'll work through this, okay? And then we'll cover some other statistical inference there. Okay, so I guess today just one question, and we'll see you guys on Wednesday. I'll post the practice quiz later on today, and you guys can take a look at that.